Welcome back. We are Wednesday, June 24th. This is the third part of chapter 16. And reminders, homework one will be due today, so tonight. Make sure you work those problems. And those are just those assigned problems that show up there on the back of the schedule and the syllabus here. So for chapter 16, homework one, it's just problems 43, 49, 51. They're listed right there. So it's just those 8 problems. You need to write those out on a piece of paper and then take a picture of it or scan it and upload that to Learning Suite by tonight. And then quiz one is also due the next day, Thursday. So after you have another session of recitation, you can work that. I'll give you some hints here on a couple of the problems on that quiz number one. So if you started to work this is part one here. We convert that trans methyl cyclohexanol to the tosylate. You should know what a tosylate is, right? So that's a para-toluene sulfonate, and it does not invert the stereochemistry of the alcohol there. So you should still have it trans, right? It only reacts on the oxygen. It doesn't invert anything there. So that's just substituting for the hydrogen that's on the alcohol. And then you got some options here. There's a couple I'm showing here. The one, sodium acetate. You should know what acetate stands for. It's charged because you have the sodium. So what type of reaction is this going to be? Right, SN2 reaction. Now that will invert the stereochemistry. So there's only one product here. And it's going to be what? The cis acetate. Now, if you want, draw out the acetate ester, whatever. But that nucleophile displaced backside attack, SN2 at that secondary spot, gives the cis now product here. And cis, this is the only one. It inverted that stereocenter. So this is all you need to put to get full credit there. And I think that one is worth 1 point. Now, methanol is a different type of nucleophile, right? It's neutral, so it's not going to do SN2. It's going to do what? It's going to wait around for the ionization here, the tosylate. Now, it's secondary. The tosylate's as good a leaving group as chloride or bromide, right? So this will be SN what? 1. And we're going to get a mixture of products here then. We can get attack from the top or the bottom, so we're going to get both here. So 2 isomers, cis and trans, for that one, both above and below. So either draw them both out or say cis or trans there in order to get full credit. Now, a couple of these is going to give a real mixture of stuff. The next reaction with this tosylate is with t-butoxide. That's an E2 type reaction. You'll get 2 alkenes there. And then the hydroboration reaction, you're going to get a real mix. There's up to 4, I think, possible isomers there, or maybe even 6. As long as you draw out 3 or 4 of them, or just 2 of them on that second step for the hydroboration from this guy, you'll get full credit there. So there's a lot more products here for that. And then this one with the cyclohexene, methyl cyclohexene, there's 4 reactions you need to go through there: Markovnikov, anti-Markovnikov. And then this one, bromination. So Br2 here, what are you going to get? You're going to get bromonium ion, top or bottom there. But the 2 bromides are going to be trans to each other. And this is a chiral product, so it will be a mixture of enantiomers. You can say plus, minus, or DL, whatever. So the bromonium ion can either form on the top or the bottom, and that will give you the 2 different. But make sure your 2 bromides are trans to each other. You get full credit there. Then we got number 2 is a couple of harder naming problems. And the second one here, or no, the first one, yeah, the first one's a long chain thing, which is a heptenol. And the heptene is counting this ethyl group here on this alkene to get the longest chain. It's a heptene. And the alcohol gets the highest priority. But then you've got to name this methyl chloro group as a substituent on the heptene. And we didn't have you do that in 351. This is called a compound prefix name. So at that position, and I think it's what, the 5 position, you've got a chloromethyl group in the brackets here. And just put it in parentheses, chloromethyl as a prefix part of the name. And then your parent, again, is the heptene all. Make sure you number it correctly and get the right stereochemistry here. Priorities here is such that I think that's an E at that 4 position. Yeah, that's an E alkene right there. And I think it's R for the alcohol at the 3 position. Anyway, and then the rest we can help you out with that, either office hours or recitation. But there's some tougher problems there. They're designed to help you review the concepts from 351. That's what quiz 1 is intended for. Okay, very good. Let's get into the topic today, which is the 1214 addition here to polyenes. And we're going to look at the simplest substrate first, which is just butadiene. Then we'll get into some substituted versions here. Let's look at another symmetric polyene first, this cyclic one. So cyclopentadiene, this would be called. And let's do the reaction with HCl. And we're going to just do 1 equivalent. If it's just shown 1 equivalent, it's implied to be 1 equivalent. You can add excess of this and get a different type of product. So, but just after 1 equivalent, we're going to limit the amount of the time here, and the product is going to be this. It's going to be 1 alkene still there, and what? The chloride is going to be at that adjacent position. It's an allylic chloride. And that's the only product, okay? 100% of the product is that. It's not 100% yield, but it's high, okay, for this allyl chloride. Well, it's not this product, okay? So let's make sure we differentiate here. We've got some selectivity issues here. We could think of hydrochlorinating right here, right? And having this non-allylic chloride product. It's not that. Okay, so why is it not that? Let's examine the mechanism early on here and get an idea for this. So where are we going to put the proton? Okay, so let me draw the molecule of HCl that way. And let's use our alkene electrons to attack that. Okay, so it's a proton donor. You could just draw H plus there if you want to. But actually in the condensed phase, if you don't have water available, HCl is a covalent compound. It's when you put it in water, then you get the hydronium ion, the chloride anion. But it's a covalent compound, but here's the positive end of it, right? The partially negative end is here. So these electrons are already polarized toward the chloride. So make sure you can follow those electrons, okay? Remember, double-headed arrows is a movement of 2 electrons, right? But look, we're going to put the proton here, and what? That's going to leave a dearth of charge here, so our cation is going to be there. So what's our intermediate look like? It's going to be this. And I'll draw the hydrogen there and the cation, okay? So what is that? That's an allylic cation, okay? Notice we did not put the proton at the internal position. That would have given us this cation. Yeah, that's a secondary cation, and so is this one. They're both secondary, right? But what is this cation benefiting from that this one is not? What is it? Resonance, correct. This one has resonance structure here. We can delocalize the electrons over there. And, you know, this is a symmetric example. We call this a degenerate pair of resonance structures in that they're both the same, but it's stabilizing this molecule overall. We can't draw any resonance structures here, okay? We don't have the alkene adjacent here because we put the proton there. We've got an sp3 hybridized carbon right here. Here we have the sp2 hybridized carbon being the cation right next door to the pi system, okay? So the allylic resonance is in effect here. If we regioselectively protonate this end, okay? Give the cation right there. And then how do we get to the product? Well, either one. These are both the same, right? Chloride can attack here, and voila, you've got the allyl chloride product. We have the chloride here, and again, this is not being formed. This one would lead to that, which doesn't have the resonance stabilization. Resonance stabilization is even better than a tertiary carbocation, okay? So remember, carbocation stability goes like this, right? The least stable is primary, secondary is more stabilizing, tertiary is even better, and then allylic, okay? So, and if you have a combination of these two, so here we have a combination of secondary and allylic. Here, if the bottom there, we just have secondary with no allylic stabilization, okay? And this can be significant, okay, this degree of stabilization for the cation there. So not that one, and what we get is it. All right, let's get another panel here and look at butadiene, okay? And we're going to look at butadiene with a couple different conditions here. These are very fast reactions. Let's look at HBr at minus 80 degrees, okay? And what we're going to get is protonation out on the end there, and the allylic carbocation. So I won't draw the proton, we just put another proton out. This just now becomes a methyl group, right? Allylocation right here. Now we could attack a couple different spots here, right? Because now we're not symmetric like with cyclopentadiene allocation. Now we have a methyl group on the end, secondary here, and primary here. That's the big difference now moving forward for 1,2 versus 1,4 addition. Even with the simplest one, butadiene, we've got this issue of first, regioselectively protonating. We don't want to protonate the middle carbon here. That would give the isolated primary carbon. Make sure you see why that pathway is not operative. Protonating here on the end to give the more substituted carbocation. That's Markov-Nikov addition, by the way. So that should relate to what we've seen before. And then we've got the resonance forms here, secondary versus primary. So what are the two products there? We can get this product, plus we can get this product. Let's see, at minus 80 degrees, it's 81%, that one, and 19% this one. Okay, now let's label these based on the mechanism. So we added the electrophile, the proton on the 1 position, and the 2 positions where the nucleophile was. So we call this the 1,2 product, and we call this what? The 1,4 product, okay? Now this is different than just simple Markov-Nikov, anti-Markov-Nikov to an isolated alkene, okay? Because now we've moved the double bond over to get this 1,4. And by the way, 1,4, 1,2 does not refer anything at all when we get more complex ones to the nomenclature. We're referring to the mechanism of where the electrophile went on relative to where the nucleophile goes on. So 1,2 versus 1,4. 81%, 19% at low temperature, okay? Minus 80 degrees, very low temperature, Celsius, whatever. This is a cold bath with dry ice and acetone, cooling that flask down. It's a very fast reaction, still done pretty quickly. Let it go for 20, 30 minutes. You'll get 81% yield of that, the 1,2 product versus that one there. Now let's warm it up a little bit. Let's do it instead, all the same, but at 25 degrees. Now here's where things get a little crazy, right? So we get the same products, but this one, that's the secondary product, this 1,2 addition, is now 44%, goes down. And we have this one again, the 1,4 product, being major, 56%, just by raising the temperature. So we're getting more addition here instead of here. So what is going on here? So we're going to call the 1,2 one at low temperature the kinetic product. Kinetic, referring to what? The rate of the reaction. And we're going to call the 1,4 the thermo product. Okay, thermodynamic product. There we're referring to the stability of that compound. So you already might see what we're getting at here. Kinetic product at low temperature, that's where more of the positive charge is, the secondary position. There's less character of this resonance structure with the positive charge at the primary spot. That's less stable, but it's still there, okay? But at low temperature, the faster rate of the nucleophile is going to be at the, what, more substitute cation spot. Thermodynamic means what? The alkene is di-substituted here versus monosubstituted, this terminal alkene. So there's two factors. At low temperature, it's the relative rates of the addition of the nucleophile, whereas at high temperature, it's the relative stabilities of the two products that dominate. So that implies something about at higher temperature, we get more reversibility. And so what do we need to do? We need to do another experiment at higher temperature to see if this hypothesis plays out, right? So let's see, what temperature should we do this at now? Let's do it at 50 degrees. So all the same here, same starting material, same reagent, but now 50 degrees C, okay? Or you can do it at 80 degrees C, but this is kind of the differentiation we're going to use. You say minus 80 or minus 78, you're going to be doing the kinetic product, okay? If you higher temperature, 50 degrees or 80 degrees C, we're going to be in the thermodynamic range, okay, the 1,4 product. And let's see if this bears out. What do we get? Oh, we get 15% this one, a lot less. That's going with our hypothesis, right? And we get this one as the dominant one. What is it? You can get it 85%. Look, it switched over almost completely there, right? So indeed, the higher temperature, the thermodynamic product begins to dominate, and that's what we're going to do. Let's see if we can draw an energy diagram now that explains this a little more clearly. And there's one other factor I need to mention here, and that is the reversibility at higher temperature. So how do we get, if it's faster at this 2 position, how do we get any thermodynamic product at all? Well, when we raise the temperature, we can reverse the formation of the 1,2 product. And that is an allylic halide. And the halide bond is not that stable, right? So we can ionize that back off. And at higher temperature, we get this reversibility effect, okay? And you can see why that is with the higher temperature, right? But let's draw an energy diagram here and see if this makes some sense. So here's our energy going up, this axis. Let's start out with our butadiene and our HBr, okay? So that's our starting point for our thing, and let's protonate and form our allyl-cation, okay? And our allyl-cation is indeed, the same one, leading to both products, right? And it's uphill in energy. We had to put that proton on there. We put it on the end. And that's the key thing at first. Make sure you protonate correctly to form the more stable carbocation. We could have protonated what? At the 2 position, that would have given a primary carbocation. So that's the first thing to do when you do some of these tougher problems. Make sure you protonate it correctly to get the more stable cation. It's always the allylic cation. And the more substituted one is going to be the key. So here we are. And let's see, we can then go down here and attack our bromide on there. And what are we going to get? Well, let me keep it oriented the same here. We're going to get this product. Okay. And that's indeed our 1,2 product. And that's more stable, you see, than the starting material. So there's our heat of reaction. It's a favorable reaction. There's our delta G. And here's our transition state leading to that, okay? It is faster, right? So, yeah, once we get the allyl-cation, here's the slow step, right? Here's the really slow step. This is faster, right, because it's lower in energy. So hopefully that part of the energy diagram makes sense. How are we going to account for the thermodynamic 1,4 product, though? Let's see. If it's 1,4, the alkene is what? Disubstituted alkene versus monosubstituted alkene. It's a monosubstituted alkene. So the 1,4 product is going to look like this, right? And because it's disubstituted, there's 2 carbons on this alkene. So the energy of this is what? Going to be lower than the energy of that. That's why we call it the thermodynamic product. So we're coming down here to this. And there's our difference, our delta G, we could say, between these 2 products. But what about this transition state leading to this one? Look, it's going to be a little bit higher than that, okay? But look, it goes to the more stable product. So at low temperature, what are we going to get? Let's draw some arrows here. Low temperature right here. Sorry, I've got a crossover there. Low temperature means we have less energy available in the system, right? So where is the nucleophile going to want to add? It's going to want to add right here, right? Because there's more secondary plus charge right there. That's going to be faster for the addition, okay, for the nucleophile. And our nucleophile is bromide, right? It's the same for both one. But you see, that's the transition state here that's quite a bit lower, right, than this one here. So at low temperature, we're going to get mainly this, okay? The addition of the nucleophile at the more substituted spot. We're going to get that 1,2 bromide. If we have more temperature available, though, we can begin to breach this barrier here. This is the high temperature thing, okay? And fine, we have more of that going here. And notice that's the more stable product. But you see, if at higher temperature, we get this beginning to what? Reverse. And that's the key right there, I think, right? So higher temperature, even though you're forming more of this kinetically, it's faster still going here. You can then break this bond and go back to this, right? And then adding here is indeed slower, okay? But once you breach its barrier, you go down to this more stable product, right? And this difference here and here is this 85, 15% under reversible conditions, okay? So this product here is formed under reversible conditions at higher temperature. So that's what we mean by the whole 1,2 versus 1,4. And this is a difficult concept. This goes beyond 351. This is our first big departure reactivity-wise. And it has to do with these conjugated polyenes, and we'll stick with the diene. You can do a similar analysis with trienes and tetraenes, by the way. The faster rate here, well, it's always formation of the more stable allyl cation. At low temperature, faster addition here. Higher temperature, faster addition here. Okay. Now, let's do a group activity here. If you could move over to the sideboard briefly, let me draw a reaction here. We're going to do a group reaction with isoprene. And we're going to have HCl here adding the isoprene. We're going to have to draw the products. And the first scenario we're going to do is minus 80 degrees. And then we're going to do room temperature or higher temperature with this also in a separate type of reaction. We're going to draw out the two products and rationalize which one is formed first. So what you want to notice here in isoprene, there's a methyl group at the two positions. So are we going to protonate here or here? This is the key. Where do you want to protonate? Okay, the first thing to notice is going to protonate here. Why is that? If we put the proton there, we're going to generate this allyl cation. That's tertiary now and primary. We can draw out the other resonance structure for it. We're not going to protonate this end over here. If we protonate there with the proton, look, we're going to get secondary. And what's the resonance form here? Primary. So even though this is a simple departure from butadiene, this makes it a little more complicated in that you've got to pick the correct side that you're going to protonate your diene. Either here on the side of the methyl, yeah, that'll be the tertiary one. You got to analyze it. You got to experiment with it. Tertiary primary versus what? Secondary primary. So which one are you going to go through here? So let's have the camera go back up over here. And there's this worksheet, this class worksheet, activity sheet, and there's a separate file on Learning Suite that will have these on them. We won't do one for every chapter, but this is a good point to pause your video and try to work through these. So there's isoprene at minus 80 degrees and isoprene at room temperature, and see if you can rationalize those two products. Look at that tertiary allyl chloride, 90%, whereas at higher temperature, it's the tri-substitute alkene product. And you might want to rationalize this next part here. Why are these other products not formed? Go through that. And then the second one will be where we have two methyl groups on the end of butadiene. And there's actually a little twist there, a little surprise. Don't get too used to the idea that everything at low temperature is always 1,2 and everything at higher temperature is always 1,4. That's actually an incomplete summary of these type of selectivity reactions. There are some substrates where at low temperature, it's actually the 1,4 product. And at higher temperature, it's actually the 1,2 product. And that's this part 2 here. So provide a better explanation for the thermodynamic versus the kinetic process. Okay, we'll see if we can do that. So pause the video and work on those. Okay, we're back. And let's work through this problem 1 here on the board. So at low temperature, what do we have here? We have more positive charge at the more substituted spot here. So our chloride would just attack there. And what's our product? Yeah, that. And what's the yield there? It's 80%. What does it say on the overhead? Sorry, you don't have to go back to it. 90%, yeah. So minus 80 degrees, yeah, 90% yield. Okay, and 1,2, and that's fine. I mean, most of them will follow that paradigm. But you should see we're forming the more stable allocation, and we're attacking at low temperature at the more substituted spot. So that's where it's going to be faster, okay, because there's more positive charge there, okay? But if we're at 25 degrees, we get this product, which is, what's the yield there? 85%, yeah. And that's what, 1,4. And that makes sense. This is a thermodynamic product. This is mono-substituted. This is what? Tri-substituted. So that's going to highly favor more of this product under reversible conditions at the higher temperature, okay, giving the more substituted alkene. Remember, alkene stability has to do with how many carbons are around there. And that's what a consequence of hyperconjugation. There's more carbons around this alkene that can help stabilize that alkene relative to this one. So this one happens faster at low temperatures, 1, 2. This one is a more substituted alkene, higher temperatures, 85% yield, okay? So yeah, I think that was good on that one. And some of these other products that you can see that are not forming actually come from this right here. So, you know, you're not going to form this product because that's the less stable allylic cation. So that's not one there. You're not going to form this one. Again, that comes from the less stable cation there. So you're not protonating it correctly. The others were protonating the middle carbons here, okay, that aren't even allylic cations then. So there's 4 products there that you should be able to rationalize are not being formed. All right, what about this other one where we get the thing switching over, right? We've got a different substrate here. We've got butadiene, but there are 2 methyls on the N carbon there. So what are we going to do with this one? Let's see, HBr. And you're given the 2 products there. Let's see, HBr. First one's at minus 80 degrees. Good. Well, the same thing here. We're going to protonate out on the end there. We're going to get this as our carbocation intermediate. Now, why do we say that one? Well, if we protonated here, we'd get secondary primary. If we protonated out here, it's the correct pathway, we get what? Secondary, and if we do the resonance structure, we get tertiary also, okay? So draw the 2 resonance structures, rationalize why this is the only intermediate allocation. It's the most stable one, okay? But now let's see. Let's draw the resonance form of this, which looks like this. If we draw the resonance form, putting the double bond over here, look, we got our tertiary cation here, and that's where most of the positive charge is going to be with this system, right? Because we have the 2 methyls on the end. And so the product here is indeed this, right? I think that's the correct one on the sheet up there, and it's 78% yield. And that's not the 1,2 product, right? Here we added here and then here. That's a 1,4 relationship. That's a 1,4 thing at low temperature. But indeed, for this substrate, that's the kinetic one now, okay? Why? Because the substitution pattern's different. than the ones we've shown. And most of the ones in the book at the sophomore level here, it's always 1, 2 is the kinetic product. 1, 4 is the thermal product. But that's actually not correct. How are we going to modify our understanding of this? At low temperature, we form the nucleophile going to the more substituted carbocation. That's really the correct description of this kinetic process. The nucleophile always goes to the more substituted carbocation, regardless of whether it's a 1, 4, 1, 2. So sorry about that. I know the book likes to give you very simplistic things you can hang your hat on, but 1, 2 is not always the kinetic product. You need to go through it and do the process. So 1, 4 in this case anyway, you're given the product there. Let's see if we do this at higher temperature. Look, we've got the resonance form here. We're at the 2 position. We're at higher temperature. The trisubstitute alkene's right here now. And what's the product at higher temperature now? At what temperature? 25 degrees. Okay, this was at minus 80, right? 25 degrees. This is our major product, 81% yield. And indeed, that's the 1, 2, 1, 2 product. So the better thing here at high temperature, what's our better summary of this reaction? High temperature is reversible, okay? And the nucleophile goes to the less substituted. And we always form the more substituted alkene. That's a better summary of this comparison between these 2 reactions. Low temperature, the kinetic process, nucleophile always goes to the more substituted allylic cation spot, gives the less substituted alkene, lower temperature, okay? Because the rate determines things here at low temperature. Higher temperature, it's the more substituted alkene that's being formed under reversible conditions. So that's a tricky thing about this reaction. Let's do one more here, a couple other examples maybe, and see if we can lock this idea in here and see if we can do this. Let's give you another substrate, see if we can get this down. Do this one. So how about this one? HCl at minus 80 degrees. And the same thing here at 50 degrees. Okay, so it's a different substrate. You've got to analyze which side you're going to protonate on and which allyl is going to be the most stable, and then where are you going to add the nucleophile? Again, these are all just one equivalent of HCl or HBr, and how are we going to do that one? Yeah, so you should protonate out here. Your intermediate should look like this. Why? Because that's tertiary and secondary now, okay? If you would have protonated over here, that would have been secondary and primary. Make sure you go through and analyze each of those routes and see what's going on. So at low temperature, where are we going to attack? Secondary or tertiary? Okay, so most of the time you can rely on low temperature is going to be 1, 2. Okay, and here it is. Here's the 1, here's the 2. So what's our product here in this case? Yep, that's the product. It's 85% this product, okay, at low temperature. Raise the temperature, and you know, you can just show the major one. You'll get full credit on a quiz or the test. That's what we're just pick the major one. There is some of the minor ones produced, but this one by far, like I said, higher than 80% yield is that. So 1, 2, yeah, low temperature, we're good there. What about here? So resonance structure would be this. And notice this resonance structure goes over to the secondary spot, but now we have a trisubstitute alkene versus what? A disubstitute alkene. So at higher temperature, we get the reversibility effect, and our nucleophile adds where? Adds right there. And that is formed in 75% yield. You can get that. And we call that the 1, 4 product, right? 1, 2, 3, 4. So there's where our electrophile added out here. There's where the nucleophile. Why? At higher temperature, it's a thermodynamic product. This one is a more stable product than this one, but this one forms faster at low temperature. This one, due to the reversibility, effect at higher temperature. This one is our favorite product. Okay. So you should be comfortable with those factors: the stability, the substitution on the cation, and the substitution pattern of the alkene. You have to keep those straight. So very good. Let's see, we got a few more minutes. Let's start to talk about the Diels-Alder reaction. So, work more problems. There's some great problems in the chapter there to work on that. And I'd like to start by reminding you of this. If you can see the overhead real quick. I showed this first day of class, synthesis of Tamiflu. And this first step right here is this reaction right here. So we have butadiene with this unsaturated ester. This is a trifluoroethyl ester. And this ester has a carbonyl. It's actually conjugated to that alkene. That actually helps this reaction. This gives a 97% yield of this product, which is a cyclohexene, and 97% enantiomeric access. That's what the EE stands for. You notice this is a stereocenter. This is a chiral molecule, Tamiflu. This is the enantiomer, the isomer that has the high activity to prevent viruses from merging with endothelial cells in the air passages. That's how it works. The mechanism is known. This drug is actually quite recent. It's only 20 years or so old now. It's a great example of rational drug design. I'll mention more of that when we get into the protein thing. But this first step right here highlights the utility of the Diels-Alder reaction, forming a cyclohexene. And you see the cyclohexene core of the drug. That's maintained throughout the rest of the steps here. But we're only going to talk about this. We're not going to do asymmetric and enantioselective versions. This is a chiral catalyst. You need the chirality to be transferred from the catalyst to the chiral product here. We're only going to worry about simple examples that are stereoselective, and the endo rule will do, but we won't do enantioselective processes. But that shows you some examples. And there are other examples here in Woodward's cortisone synthesis, which many years before, R.B. Woodward's considered one of the greatest scientists ever. He could have won 2 or 3 Nobel Prizes if he wasn't a chain smoker and died quite young. He earned his first Nobel Prize when he was in his 40s. He was a professor at Harvard and did a number of landmark syntheses. Very complex molecule for the 1950s when he first did this synthesis of cortisone. But the key step here was the Diels-Alder reaction. Here's butadiene with a dienophile, the alkene here on the side of this quinone, to give this product right here. And that's kind of the core that goes on to the AB rings of the steroid. So there's many more steps here. We're just showing a portion of the synthesis there. But let's get into the Diels-Alder reaction here on the side here. And again, we'll finish it up next time, but we need to talk about the basics of the Diels-Alder reaction. It's named after 2 German chemists, Diels and Alder. Diels was the professor. Alder was a graduate student in Germany in the 1920s, before World War II. And the student shared the Nobel Prize with his mentor. It's kind of a unique example of a Nobel Prize thing. But at first it was kind of an obscure reaction. Nobody really saw the utility of it. They won the Nobel Prize many years later than when they did the work, of course. But some others, Corey and Woodward, like I showed, started to use their reaction for complex synthesis. And people saw why it was so important. So the Diels-Alder reaction, DA, whatever you want to call it, involves a diene, okay, 2 components to this reaction, plus what's called a dienophile, okay, dienophile. And what does that mean? Phile means to love or to want. And so the dienophile wants what? Wants a diene. It's kind of a simple designation of it. And how does the reaction work? Well, just push the electrons around the ring here. And what we're doing is we're breaking these pi bonds, okay? And we're making what? Sigma bonds here. And the new sigma bonds are right there and there, okay? So it makes a cyclohexene. But you can see the pi bonds kind of went away. Well, one of them's still there, right? So what did we lose? We lost a total of 2 pi bonds here. 2 pi bonds went away. Each pi bond's worth about 60 kcals per mole. So that's costing us about 120 kcals to break 2 of them. Overall, we get this one back. So I'm kind of keeping track of which bonds we're losing there. But what bonds are we getting here? We're getting the 2 sigma bonds. And sigma bonds are worth 90 to 100 kcals per mole, quite a bit more in stability, right? So if we're forming this new sigma bond between the 2 carbons, that's lowering things about 200 degrees. So that's the exothermic part. As we form that, right, that's giving off that heat. So what do we get overall? What's the change in free energy here? What is it, about minus 80 or 60 kcals? So this is a favorable reaction because you're only breaking a couple pi bonds and you're getting 2 sigma bonds out here, and you're creating a cyclohexene. So this is an unusual reaction, isn't it? It's not SN2, it's not SN1, there's no carbocation intermediate, no radical intermediate. What type of reaction? So the diene has to be in the proper conformation in order to get this reaction go. It has to be able to rotate around here. This is the more stable form conformationally, the S-trans of most dienes. It's got to be able to rotate around. And that difference is only about 2 kcals per mole difference in most dienes. So the S-cis is the one that will go on and do the reaction to form the 2 new sigma bonds and moving the pi bond over to form the cyclohexene. Let's look at a few simple examples here in our last couple of minutes. And we'll go into more detail, of course, next time in our second hour here on Wednesday. So let's look at a couple examples. Let's do a reaction here, the simplest Diels-Alder. So can this reaction work just with ethylene gas and butadiene? It turns out no. This is a bad combination here in the gas phase and being able to do this reaction. This dienophile here, because it doesn't have the electron withdrawing group, it turns out that this LUMO energy, this higher unoccupied orbital, matching with the HOMO of this. Maybe we'll get into some of that orbital interaction comparison there. You've got to have a substituent on the dienophile in order to get this reaction to go. So no reaction for that one. But if we've got this combination, which is this dienophile now with an aldehyde here. This is called a Crolian. This is a good, stable liquid molecule here. This is a liquid here. And let's go ahead and do the Diels-Alder reaction, push the electrons around there. And what product do we get? Yeah, we get the cyclohexene aldehyde product. Good yield. And notice there is a stereocenter right here. This is a chiral molecule, but we form both. Okay, so it's racemic DL, whatever. Let's look at a couple other simple examples here before we wrap up. If we've got this with 2 carbonyls conjugated to the dienophile, we've got this is called an anhydride here, maleic anhydride. Don't worry about the common name for that. But this helps activate. This actually lowers that LUMO energy to almost be the same energy as the HOMO energy of the diene. And this Diels-Alder goes like a shot. This will go, don't even need to warm it up. Some of these you need to warm up a little bit. This one will go at room temperature or even lower. And what do we get here? We get the cyclohexene product, and that anhydride is still there, right? So keep track of which bonds you make each time, and make sure you know where the X group ends up. So the X group doesn't end up here. It ends up right there, right? So this aldehyde cyclohexene that's formed is this one. And same thing here. But we need to talk about this. These 2 hydrogens are what? Cis to each other in the starting material. So what do you think here? These 2 hydrogens right here, are they going to be cis or trans to each other? That's right, they're cis to each other. So make sure you either draw them both up or both down. Now this molecule, is that chiral, this molecule? No, this has some symmetry, a plane of symmetry right there. It doesn't matter whether you attack from the top or the bottom there. But these 2 hydrogens need to both be up, or if you flip it over, they're both down. But it has to be there with that cis arrangement between the hydrogens here. So we'll leave it there. We'll do some other simple deals, alter actions to start out. And we'll do some a little more complicated ones next time for the second hour here that we'll look at that. So stay tuned for that. Very good. Let's take a break.